This is Professor Hill, and what are we going to do today? We are going to try to learn more about water and ocean structure. I want to start by reviewing a little bit of things I talked about in the last one because I decided I wasn't thorough enough. This is a simplified version of that graph I showed you where we were talking about latent heat. So here we talked about the latent heat of vaporization and where water's going from liquid to a gas without changing temperature. Heat's being added, but it's not changing temperature. And I like this because I added that it's both the latent heat of vaporization, but it's also the latent heat of condensation because it can go either way. If you have a gas and you're losing that amount of heat, it will turn into a liquid. If you have a liquid and you gain that amount of heat, it turns into a gas. So I wanted to add evaporation or condensation to that part. And same with the latent heat of fusion. Fusion makes it sound, just like it's turning into a solid. So when a liquid is losing a certain amount of heat, well, water, we're talking about water, is losing a certain amount of heat, it's freezing and it's becoming a solid. So it's losing energy, but it's still staying liquid until it loses enough that it turns into ice. And conversely, that same amount of energy, that latent heat, because heat is just energy, of fusion can be added to ice without changing the temperature until it hits the point where it melts and it becomes a liquid. So I just wanted to add this and be more thorough. I went back and changed that particular page of the PowerPoint to add, evaporation or condensation and melting or freezing. I don't know if I added this diagram, but I hope I did. All right. So now we're going to go on and we're going to talk about properties of fresh water. We're not actually going to do this part today. We're going to just see if we can get density done. Density's actually got a little bit of things going on for it. But first let's talk a little bit about the difference between fresh water and salt water. Well, sea has salt in it. We all know that. Salts, let me give you a definition of salts. A salt is when you have ions, and ions are elements that are either positively charged or negatively charged. If it's positively charged, it's called a cation. If it's negatively charged, it's an anion. I won't ask you that on a test. I'm just being thorough here. So you got your cations and your anions. And because they're positively and negatively charged, they're attracted to each other. And when they become one, that is called a salt. So when you add two ions together and they become a neutral third thing, it's a salt. The salt we know best is the addition of sodium, which is Na, it's positive, and chlorine, which is negative. You add those two together, sodium, oops, I should say plus, not plus, I got to change that, plus chloride is sodium chloride, which is halite, or what we know as table salt. Plus, not plus. All right, so the other thing this diagram tells you is if you've ever had a mouthful of seawater, it seems very salty, right? Because mostly you can see that like 85% of it is salt, okay? On the other hand, seawater itself is 96%, more than 96% water. Only 3.5% of it is salts. By the way, that will show up on a test. You should know approximately how salty seawater is by the time you're done with this. And that is by no means universal. It is not 3.5% all the way through the ocean, but we'll get to that in a minute. Anyway, there's a bunch of other ions in seawater that also make different types of salt. But they're much less than the sodium chloride. So again, it tastes salty to us. I will not ask you all these ones. I will expect you to know about sodium and chloride because they're the main ones. You should know that there are other ones. If I ask you true and false, is sodium chloride the only salt in the ocean? That would be false, right? but I wouldn't expect you to know sulfate, magnesium, all that stuff. Okay, another thing about having salt in water is it lowers the it makes it so that the temperature has to be lower in order to freeze. If you've come from a cold climate like I have, you know that if you want to melt ice on your sidewalk, you throw salt on it. Why would that happen? Well, basically because sodium chloride is made of those two ions, right? And we talked about water being polar, having a positive and negative end. So what can happen is the sodium chloride breaks up, and they can grab parts of the water, the positive and the negative ends, and pull them apart. And so it makes the ice melt. But you can freeze water. You just have to get it colder than you would fresh water. You have to get it at about 29 degrees Fahrenheit. Do you know what temperature fresh water freezes at? 32 Fahrenheit. Okay. So let's talk about temperature and salinity of the ocean. This is a cross section, right? This would be like if I cut a slice through the ocean and looked at it. This is actually a temperature diagram done on the South China Sea for somebody's research they were doing. You can see that blue is colder and red is warmer. In general, the ocean is warmer at the surface and gets colder with depth. That's pretty intuitive, right? You know, the sun shines at the surface, it does not shine at the depths. But it is, you know, by no means like this everywhere. There are places where the cold water comes up. That's called upwelling. And there are places where the warm water goes down. That's called downwelling. More on those later. This is a really cool map showing you average temperatures in the ocean. Blue is cold, red is warmer. Notice the red layer is by the equator, which gets the most sun. There is a really neat video. Let me just kind of get it over here so you can see it, right? A little rotation of the Earth to kind of show you where it's warmest. Not big surprise that, you know, the Red Sea, which is near the equator, in between all those deserts and very small and shallow, is going to be warm, right? And again, it's mostly around the equator, right? There's another video that I like even better. If I can get it to come up. Here we go. Oh, this isn't the... Nope, it's the same one. Oh well. All right, so anyway, this is pretty intuitive, right? Hotter where there's more sun, colder where there's less sun. Now let's talk about salinity. So ocean salinity is how much salt is in the water. We measure it in practical salinity units, which is abbreviated PSU. PSU is measured in parts per thousand, or for example, grams per kilogram, right? Because 1,000 grams make 1 kilogram. And so this little symbol here, which you may not have seen before, when you're doing your labs, if you see that, it means parts per thousand, which is what PSUs are measured in. The normal range of ocean salinity is between about 33 to 37 PSUs, parts per thousand. Now here I'm going to show you a pretty neat video. This, I think, is the one I was looking for earlier. And you see that the blue is the lower. We said 33 to 37 is normal, right? But it can get lower than that, you know, especially if fresh water is coming into the ocean from a river, for example. So we've got 30 is dark, and as they get more saline, higher salinity, they become more yellow. All right, so we've got a video that shows you the salinity of the world over a certain time period. So remember, yellow is more saline, blue is less. Now, if you're wondering why it's going back and forth on the top, that's when it's winter time and it ices over and they can't get measurements. Okay, it's not like the salinity is falling off the charts. It's just that parts are icing over. Now, if you look around, you'll see there are some blue areas. They seem to get blue far north, right? We got blue around Alaska, blue up here. Well, this is probably coming from the Hudson Bay, right? That's a lot of fresh water that comes out. But there's a lot of, there's rivers up here that don't, in the wintertime anyway, that in the past, that area has always been iced over. Due to climate change, it is now opening up and they can get measurements. But if you look around, like right here, this is not due to rivers. This blue right here, where it's showing you that it's getting less saline, is because that area of the world right above the equator, they get a lot of thunderstorms there. So thunderstorms, right, are going to be raining fresh water into the ocean. And so whenever there's a thunderstorm, it's going to dilute the salinity. Notice here, these two places, this place right here, and there's a few spots around India. If you pick one of those spots where you see the blue coming out, just sort of focus on it and try and, I'm going to show you another map, and I want you to see if you can spot a river coming there. So pick a spot where it's blue, not this one though. And the next map, let me get this out of here. Well, let me just move it for a minute. The next map shows you major rivers of the world. All right. So, for example, the Niger and the Congo come out here in West Africa. The Yangtze and there's the Mekong come over here in the east coast of China. And there's a bunch of rivers that come out on north of Russia, but again, in the past, it's been iced up there. Climate change will change that. All right. Now let's get more college level graphs here. Okay, so salinity. Well, let me see if I always like to, look at the X and the Y bar of my graphs first. Salinity. We're measuring salinity, low to high. And we've got green is going to be salinity and red is going to be temperature. Then we look over there at latitude. So latitude is what we're looking at here, right? Hopefully you understand latitude by now. It's these east to west lines that we've arbitrarily put on our planet basically so that it's easy to sail or fly over the world and know where you are. The equator's in the middle. It's 0 latitude, and then you go from 0 to 90 degrees north is the North Pole, so they made it go 0 to 80 here. And for example, this is 60, and they have it lined right up with 60. This is the Tropic of Cancer. It's at 23 degrees. That's lined up with the Tropic of Cancer here. The Tropic of Capricorn, in case you're wondering, these tropics are the places in the world where the sun can be directly overhead during parts of the year. So the Tropic of Capricorn, which is 23 degrees south of the equator, is lined up right here. Then we go to the Antarctic Circle, which is 60 degrees, and 90 degrees would be the middle of Antarctica. Okay, so you're looking very far north to very far south. So we see that salinity is very low very far north. It's also low very far south, but not as low as it is far north. There's got to be a reason for that. Probably a lot of rivers coming off, but I'm not going to give that away yet. So then we get to the Tropic of Cancer, and it has a bump. It gets saltier and saltier and saltier up to the Tropic of Cancer. And then it goes down at the equator. The equator goes down because of, basically, the equator has more rain than anywhere else in the world because it's hot, right? The sun is always focused on it and it is that evaporates the ocean, makes thunderclouds, which make rain, which makes the water fresher. And then it gets saltier as you move away from the equator till you get to the Tropic of Cancer. So notice these two places have the saltiest water overall. You know, this is a very generalized graph. And then it gets less salty as we go to the poles. Temperature, notice, cooler. Now this is more the same at the North Pole and the South Pole. We got 32 degrees. That's the freezing temperature of fresh water anyway. And then it gets hotter until you get to the equator. What a surprise. And then it gets cooler as you go back to Antarctica. Up here we have temperatures in Celsius and in Fahrenheit. If you need to, you know, get your bearings about what is 0. Well, 0 Celsius is actually the freezing point of fresh water, right? 32 degrees Celsius, Fahrenheit. I don't know why I did that. Yep. This is on your book, not this particular picture, but they have a really nice salinity diagram. So you're seeing that it's not as simple as this, right? It's a little more complicated than this, right? You can see that the salinity is less. They have the numbers here in this case, but blue is still less. In the north and the south extremes of our planet, it is in general saltier in the middle of the planet, but you see it's a lot saltier in the Atlantic than it is in the Pacific. And well, you'll probably figure out more reasons for that later. And then places like where a lot of fresh water runs off the continent, like this would be, oh, I forgot the name of it, the river that comes off of the Indian coast. You see it's a lot less salty there. Same with these rivers that come off of China. This is the Mediterranean Sea. It's its own little water mass. It's kind of trapped there because Africa's closing it off from the rest of the ocean. There's still like 30 miles, you know, that it can interact with the rest of the ocean, but that's not very much. It's got a lot of water in it, and it's relatively shallow, so it evaporates faster than it can exchange water with the main ocean. And so because the water is leaving and the salt is staying, it stays saltier than the main ocean. The ocean is stratified by density. Density is, remember, mass per volume. So basically how heavy the water is. So water can change. All water is not the same density, especially not in the ocean. And just like wind on the surface is created by differences in density, because that's what causes differences in pressure, right? And pressure is what causes wind. Heavier wind pushes lighter wind. Same with water. Heavier water pushes lighter water. Heavier water goes to the bottom of the ocean, and lighter water stays on the top. They eventually mix and change, but it takes a very long time. Water obviously moves a lot slower than the atmosphere. This is a very simplified diagram. I'll show it to you again later. It's actually a great deal more complicated than that. This is a slightly more complicated version. Don't have to know this, but I just want to let you know that it's not as simple as they're showing you there. And this is another simplified version, but yeah, it lets you know that everything is not as simple as I'm showing you. The reason it isn't is because we got all these continents in the way, right? If this was just an ocean planet, everything would be a lot more simple, but they have to interact with the continents. Okay, what is the density of ocean water a function of? Three main things. Temperature. Cold water is denser than fresh water until it freezes, right? We remember that? When it freezes, water is the only thing that when it turns into a solid, it's actually lighter than when it's a liquid. But cold water is denser than warm water. Salinity. This is probably pretty intuitive. You put salt into a glass of water. Do you think it's more or less dense than a glass of water without the salt? You're adding weight, so, you know, mass divided by volumes, the volumes are the same. Obviously, the salty water is going to be denser than the fresh water because it's got more mass. And pressure, you know, we can go up to 6.6 miles down in the ocean. And even though water isn't that easy to compress, when you've got miles of water on top of it, it can be compressed. So the water at the bottom of the ocean is under a great deal of pressure, and so it is denser because of that too than the water at the surface. Now this diagram is in your book on page 182. I want you to be able to, again, to understand things like this. So what we're seeing here is these lines are density, and each one of these lines, they're telling you in grams per centimeter cubed how dense the water is. Do you remember how dense fresh water was when we were talking about ice? It's at 32 degrees, it's 1 gram per centimeter cubed. So you can see that this water has salt in it, so it's a little bit denser than fresh water, right? This is the lightest, it looks like, 1.012, and this is the heaviest, 1.029. Now, we wouldn't notice this. You'd have to measure this. You'd have to be a scientist and measure this to notice these small density differences. But these small density differences cause the undersea currents in the ocean. And these undersea currents in the ocean are actually very important. They drive climate on this planet. They drive life in the marine realm on this planet, and life on the marine realm affects us even out here in the desert. So these things are important. All this stuff, you know, is important to understand in a changing planet where we are now in the Anthropocene, where we are making global changes to our climate and our environment because of our activities. So if you don't understand any of this stuff, you won't understand what scientists or politicians are talking about. And we need more politicians that understand science to get a good grip on this climate change problem. Okay, that's me going off on climate change for a while. Okay, so let's get back to the diagram. All right, so we got these densities. We see that they are a function of, we've already talked about this, right? In the very last thing, we said that pressure and temperature and salinity affect density. So we see here temperature, low temperature, freezing, right, to high temperature. It's in Celsius. So here 0 degrees is freezing, and 25 degrees is, oh, I don't know, about 75 degrees. Down here we have salinity in parts per thousand, 33 to 36. Okay. All right. So what are we learning here? Well, okay, it says note different combinations can lead to the same density. Let's not worry about that. Let's just take a number. We're going to go with 33 parts salinity, so low salinity, and let's just look at it, what the density is at 20 degrees Celsius. Okay, so we go up there and we go, okay, it intersects the 20. If I drew a line here with 20 and a line here with 30, they'd intersect right here, and I would say, okay, the density there is 1.023 grams per centimeter cubed, and that's perfectly valid test question. I would expect you to be able to read this and tell me what the density is. Now, okay, so that's how dense it is. If it's 33 parts per thousand salinity, PSUs, at 20 degrees. What if I follow this 20 degrees over here across until I hit another line? Okay, now it's more dense, right? It just went up 0.1 thousandth of a gram. All right, so my little thing. Okay, so it went there. So now let's see what salinity is. What is the salinity? Go back here. Salinity. All right, so now it's like 34.75. So the density went up because the salinity went up, right? Because the temperature stayed the same. Let's see. Okay, so I can go up higher, the temperature 20 degrees. If I go way up here till it hits this, okay, went up again, you know, it's more dense, and the salinity is higher. All right, that makes sense, right? The temperature stays the same, but we add more salt, it's going to be more dense. Let's do it the other way. Let's keep the salinity the same and see what happens when we change the temperature. Okay, so we're at 30. Let's go to 34. We go up to 34 at 5 degrees. It's 1.027 grams per centimeter cubed. Okay, 5 degrees. Let's warm it up a little. All right, so we warm it up till we hit 1.026. Okay, now it's warmer and it's less dense. And so we warm it up a little more. And we say, look, it's getting less dense the warmer we make it. Okay, so that's another relationship you can see out of this graph. So, you know, if I gave you this graph and I said, how does salinity affect temperature or affect density if you make it less saline or more saline? You should be able to look at the graph and say, okay, you know, I would say you have to keep the temperature the same. If I add more salt or less salt, is it going to be more dense or less? Well, you might be able to figure that out without looking at the graph. But if I said, let's keep the salinity the same and change the temperature, you probably have to look at the graph to figure out, oh, I see that as it gets warmer, it gets less dense. But you should be able to read that off this graph. So if you have troubles with this graph, feel free to contact me and we'll talk about it. That's just something to give yourself a quiz. All right, this one's a little more complicated. Because remember I said there was 3 things that affected density: salinity, temperature, and pressure. So we've got our kind of our graph that we just looked at already. But now we've added this. What is this? This line is showing you, this is the ocean surface and this is the sea floor. And what we're doing is we're finding out as we go down with depth, because as we go down with depth, what happens to the density. So we see that it's not a straight line. Okay, we start here and we just take a drop of water, right? And we're going down. It's getting, let's see here, this is 500 meters. All right, at 500 meters, it's a little bit less than 1.024 grams per centimeter cubed. Now at 1,000 meters, it's a little more than 1.026. So as we go down, and then it stays kind of the same for about 1,000 meters. From 1,000 to 2,000, it doesn't change much, right? It does get a little denser, right? Now it's more than 1.027, and then it gets much denser as you go from 3,000 to 4,000. Oh, I'm sorry. I'm wrong about that. I'm not reading the graph, right? Okay, so from 1,000 to 2,000, it went from a little more than 1.026, so let's just say 1.026.3. And then when it's at 2, it's about halfway between this, so 1.0275. And then when it gets to the very bottom, it doesn't change that much. See, got to look at the graph, right? I was thinking with my head that as it gets to the bottom, it would increase a lot, but it doesn't apparently. So between 3,000 and 4,000 meters below the Earth's surface, below the level of the waves, it doesn't change as much as you'd think. So it's a little more than 1.028, but it's not as dense as 1.029. Would I put this kind of graph on a test? No, probably not. I doubt I would. But I do want you to know that density affects, pressure affects density. It doesn't affect it in a linear pattern. I guess that's what we're seeing here, right? It doesn't make a straight line. It affects it more. It looks like it affects it more higher up than it does, and it slows down as you get down. So I guess the moral of this story is, or what I'm getting from this graph is, that you can compress water, but you can only compress it so much, right? It's water. And even though you're down at the bottom and you're getting lots of pressure, it's as compressed as it can get, apparently. Okay, so K-balling. Well, I ask you to know about that. Adding together two water masses with the same density to produce a third of a higher density, which will sink. Probably not. I don't think I will put something like that on a test, so I might even take it out of here. But what's important to know, I guess that's why it's in there, is the North Atlantic intermediate water, the Antarctic intermediate water, and some Antarctic bottom water are formed that way. So I guess you should know K-balling, because I'll tell you why. You don't have to know those yet. I'll get to those in a minute. Come on. Ocean zones, masses, all right? I think I've shown you, have I showed you this already? I think so. So a water mass is a body of water that is similar. It has like a characteristic temperature and density and salinity. So in the ocean, you K-ball, you can get these two types of water that come together and form a third type. Some of these are the third type, and they become water masses of a certain temperature, a certain density, and a certain pressure. And because of that, they will float on top of each other or sink underneath each other, depending on which is the densest. Now, they tend to stay stratified. Stratified means in layers. And again, this is a very simplified picture. But these are the four main masses in the world. There's plenty of others, but these are the four main ones. I put them down here because these are the ones I might put on a test, right? You can see that the Antarctic is going to be on the bottom and the Gulf Stream is going to be on the top. There's going to be a lab at the end of this where I show you, and we do a lab on it, why they stratify like this. And it's kind of neat. I think it's kind of neat anyway. Well, I had a picture of the Mediterranean behind the Mediterranean Ocean, but it's not really that important anyway, because it doesn't really mix with the rest of the world very much. And when it does come out, by the way, it sinks. Why does it sink? Because remember, I was telling you about how it evaporates and gets salt concentrated in it. Well, more saline makes it more dense. So when it does come out of that little 30-mile opening at the Straits of Gibraltar, where it has, and it can get out into the Atlantic Ocean, it tends to sink down under the other waters. Oh, there's the lab. Okay, so this is a good time to do the lab. It'll get this density stuff, firmly implanted in your head. Until next time.